这一个，这样，就是说我这一句删掉，直接讲那个就是里面的，
如果你要删掉，不是你这个就删掉，然后写完我这句，然后放一个抖抖，那个 colon
那里 between 了，
啊，没有 start，没有 start，就这个没有记号，这个中文有记，这个记号这个
所以我也
这样没有记号，
其实我有一句嘛，
没有记号，嗯，
然后这个这什么？
好，这个哈，这我感觉知道你要写什么，但是你写出来的东西，
确实很
哎
我不懂，可是
，OK，这样子讲啊，这个东西这样的话，就是这样。OK，到这边就结束了嘛，对不对？这个就已经define 完你的 inverse map 了，对不对？但这个你写来做，你要写的是这个东西，compose 一下，compose 一下，拿回一样的东西，这边 map 去这边，
哦，
然后再用这一个 map 把这个东西 map 去它该 map 的地方，然后你就会拿到一样东西。另外一边也是这样，懂吗？就是
有懂，
算那个 composition，送回一样的地方才是 identity map，这样行吗？
对，我懂了。然后这个是算出来他买回去的方法，
就是你从这里开始
嗯，
map 过来送到这里嘛，然后这个是一个 element 在这里，再用这个 inverse map 回去。因为你这样子 define 是 inverse 啊，你没有 prove 它是 inverse 的话，我不知道它是不是 inverse。你可以 define 是任何的 map，你要叫它 inverse 也是可以，但是问题是它要 satisfy 那个 inverse 的 property。
所以我现在要 prove 这个，
没有
不是
prove 啦，就
prove 啊，就
是要
写出来。
你就先你要 you want to show that this is the inverse of I 啊不，或者说 to show that this is inverse of I，we show that I identity I inverse I 是来的，对吧？因为它 compose 起来过后，这个东西送回 identity，new identity。
差距嘛。对，这个问题是，对，也没有感觉。
什么？充电器坏？没有电？你有带啊？给白纸哦。啥？哎，哦，对， 报更新了。可以更新。
没钱都人
反正都剩最后2堂课了，应该没有什么东西了吧？应该不重要，最后2堂课，我看一下，他发你邮件啊没有吧？应该还好吧？看 期末考试那个邮件不是应该早就要发了？他们在前2周就收到，上一周还是什么？找不到哦，没有啊，你86，你还有2次可以翘，但是呢，今天上了你就1次可以翘。老师翘，对，有这几天也是很水绕一直做工，很多东西是要死的。要吃饭。电池我不能吃。有点是诶，明秀那一群，回头我们开学。Hello. All right. I have posted out the formula sheet. I think you check it on the Moodle. Okay, so you can familiarize with yourself the formula. And hopefully this week will cover finish up to divergence theorem. Okay. Yeah. So we have 5 more hours to go until the end. Any question or not from the previous lecture? Will you try the review exercise yet? You should try the review exercise because it's quite important for your exam. Yeah. Let me know if you have any issue. Doing it. Any question from last lecture? Any? No? Got try do the homework question or exercises or not? Tutorial exercises, not yet. No chance yet. No time yet. Make sure you spend some time doing again. At least one. Okay? At least one. At least. Okay? Yeah. Because these are new stuff, not the usual stuff. Yeah. All right. Okay, so let's start. Um, let's start with recalling what is Green's theorem. Does anyone know what the Green's theorem is? Anyone knows what's the Green's theorem? Green's theorems relate two things together. Okay, relate the lines integral and the surface integral. Okay. So what kind of line integral are you doing? Grace, do you know? Don't know? Could you refer back to the notes? What kind of line integral are you doing? So, do you know? Curve. Okay. Not just curve. What kind of curve? What kind of curve? Close curve. Okay. Is close enough? Huh? Close enough or not? Close curve mean what? use n at the same point. Okay, you get a loop closed curve. What else? Simple closed curve. What is simple? There is no self intersection. Okay, no self intersection. Anything else? Anything else? No self intersection need to be closed, and then okay, what kind of orientation? Two orientation, right? Go to left, go to right. Clockwise, anti-clockwise. So this is a positive oriented. Okay, positive oriented. So positive is what way? Anti-clockwise, okay, or counterclockwise. And finally, this curve have to be piecewise smooth. Okay, so that you can do parametrization. Okay, using smooth function. Okay, differentiable function. Okay, so you need all these item here. Okay, so since it is closed, right? So the closed curve bound the region. Okay, bound the region. Let me call it D. Okay, I call the bounded region D. Okay, so outside C. So in other words, this curve here is the boundary of the region it bounds. So this is the boundary. So I write partial D. Okay, boundary of my region. Okay. So what is the statement here? So I need to have two functions. Okay, call it P and Q. They need to have continuous partial derivative so that I can differentiate them. Okay. On where? Okay, on an open region that contains the D. Okay, that contains D. So meaning it is continuous, the derivative is continuous in D in particular. Then, okay, we relate two type of integral. One is line integral, the other is surface integral. Okay, so we do line integral on one side, surface integral on the other side. Okay, so what kind of line integral we're interested in? Okay, we are interested in P dx plus Q dy. Okay, I think you saw this in your ODE class, right? P dx or plus Q dy equal to 0, something like that. Then this thing have an exact solution if and only if what? P del y equals to Q del y. Okay, so later I will explain why is this true. Okay, on the other side, there's no coincidence here. You have Q del x and P del y. Okay, you can see that there's swap position here. Okay, P is on the dx, but I differentiate P with respect to y. Okay, Q is on dy, but I differentiate with respect to x. Okay, and then we take the difference. And then this is over the area of D. Yeah. Okay. So last time we see this example. So what are we really doing? What do you think? So on one side here, last time I say P dx Q dy, what's the natural way to obtain this kind of integral? What's the natural way? Before Green's theorem, what did you learn? Before Green's theorem, what did you learn? Physics. What did you learn? After line integral, what have you learned? Sorry? Conservation of energy. Okay, that one is about whether vector field is. Oh, okay. So that one is about the vector field. Okay. F is conservative. Okay. When is it conservative? If I can write my F as a gradient of some scalar field. Okay. If I can write my vector field as a gradient of some scalar field, this is conservative. What else? Line integral and compute what? Word done. Right. Okay, word done. So you can actually let P equals to F1, Q equals to F2. Then when you compute the work done, this is the integral you are looking at. Can you get what I say? So an example of this integral is you can replace this integral by f1 dx plus f2 dy. Right? Remember? What is this? This is the integration of the vector function r with dr. Alright? Can recall? Please recall. So this is the work done. Okay? You need to split your work done into dx, dy, and dz to compute. Okay, so this is an example of this form. Okay, so now your curve is a closed curve. Okay, closed curve. So you are computing a work done in a closed curve. Okay, so how do you do work in a closed curve? How do you do work in a closed curve? You need to move in a rotational manner, right? So this suggesting that the vector field is moving in a rotational manner. Okay. So this suggests that the vector field is moving in a rotational manner. Okay. So let me draw something for you. Okay. So let me draw something. So what's the idea of the Green's proof of Green's theorem? I won't go into detail, but we just get what's this Green theorem is doing. How come a line integral can relate to a surface integral? Okay. So on one side, you have a loop integral. Okay, I call it a loop integral because it's a line integral, but the line is closed. On the other side, you have an area integral of this weird function here. Okay, difference of partial derivative. Why are we looking at this, right? Okay, why are we looking at this? So one side here, what can you think? You have a loop. Okay, I call it C. Right. So this C here, how to do work in a circular manner. So my force have to evolve around the loop. Okay, my force have to evolve around the loops. Okay, so if there's a positive displacement around the loop, then I have a positive work done. Make sense or not? Does it make sense? Make sense? So if you put a dot here, then you will move around this vector field. Maybe I show you one animation here. So in the Moodle, right, you can click the link I shared in the resources area. So there's a place called vector field visualization. Okay, you click it in, and then you use that website. Okay, so if I put some rotational field, so for example, I put in this function here, x y equals to. This is the one we have seen before, minus y comma x. Okay, so there is a positive work done in a rotational manner. Okay, so if you put a dot here, then the dot will follow the particle will follow the vector field and move. Okay, so you have a positive work done there. Make sense? Hello? Hello? Okay. Okay. Yeah. So how about this area here? Okay, how about this area here? How about this? Okay. Why we connect to an area? Okay. So what you can do is you can really split this this circle here into infinitely many small circles. Okay. And do the loop integration for them. Okay. Why why if I add out all these contribution is the same as the outer one? Because you can see that the adjacent contribution will cancel, right? Because one go the different direction. Okay, so if you integrate over the loop, then the adjacent loop will cancel with the adjacent side. So altogether, we will get is the outermost circle. Make sense or not? Does it make sense? How about I draw something square? Okay, if I want to compute the C here, right? So I can, in principle, let me draw this. In principle, I can break this into 4 smaller cube. Okay, and then I go around the orientation. Okay. Okay. So for example, this one go here, go up, go there, go here, and then this one go to the use the other color, go there, go up. So for every circle I put a counterclockwise orientation. But you can see that on all the inner edge, there are cancelling happening. Right? Correct or not? If you change the orientation of the curve, the line integral will be negative of one another. Remember? Remember or not? Integrate of C equals to minus of integration of the negative orientation of the curve. Okay, so if you add out the contribution, they will cancel out. Okay, what you left with is the outermost. Okay, so if you consider all the contribution here, right? Okay, I can split them into area. Okay, I split them into area. This small circle live in an area. Okay, and then the rotational quantity will be represented by this difference of partial derivative. Okay, so if I integrate over the area on this quantity here, what I will get is exactly the loop integral. Okay, so this means what? This means that the thing inside the surface integral here calculate the rotation of the vector field. Okay, later we will call this thing a curve. Okay, how curly is the vector field? Okay, we'll call this a curve. Okay, later we'll introduce this as a curve. Okay, because what? You see, we swap the position. Okay, differentiate q with respect to x, and then I take the difference. What kind of operation is this? You swap position, and then you introduce a minus. Is this familiar enough? Swap position, introduce a minus. Linear algebra. Swap position, and then introduce a minus. Where do you see introduce a minus? Huh? Determinant. Okay, determinant. So actually, this comes from a cross product. Later we'll define in general. Okay. Yeah. So this one comes from cross product. Okay. So later we'll see it. So let's do one exercise to recall the theorem, Green's theorem. So let's evaluate this particular function here. Okay. In higher maths course, right, you will call this a one form actually. Okay, you will call this a one form. You integrate a one form. Okay. And this C integrate over the closed curve C. Okay, what is this closed curve here? This C here is the boundary of a semi-annular region. Okay, semi-annular region in the upper half plane between circles x squared plus y squared equals 1 and x squared plus y squared equals 4. Okay, so this is a line integral. What should you do? Line integral around the loops. What should you do? What do you do when you do line integral? This line live in R3, R2 or R3, or in this case R2. So what should you do? Line integral only have one variable. So you need to parameterize your curve. Okay. So if you want to try to parameterize this curve, how many number of curve you can break this into? you can break this curve into 4 parts, right? So you can break this into C1, C1, C2, C3, and C4. Okay, you can break this 4 part, and then you parameterize C1 with a semicircular curve, and then C2 and C4 are horizontal line, and then C3 is also a semicircular with different radius. Okay, but what does Green's theorem tell you? If C is a what kind of curve? 边加. What's the condition for curve in Green's theorem? Check your notes. What's the condition? C has to be C has to be what? C has to be what? Who can help? Li Kai. C has to be what? To use Green's theorem. Huh? I thought we started with what is C just now. C has to be what? Close. Okay. Is it close? So you have a loop here. Okay. Is it simple? Okay. It's simple, right? Okay. Because there's no self-intersection, and then positive oriented. Okay. And then piecewise smooth. Okay. Piecewise smooth. So everything is piecewise smooth. So piecewise smooth means it is not smooth up to finitely many points. Okay. All right. So it bounds a circular region here. Okay. So how do you let's use okay. So let me write down. So first where you can use direct method. Okay, direct method, which is to use 4 parameterized curve. 4 parameterized curve C1, C2, C3, and C4. Okay. Second method, you can use Green's theorem. Okay, because this is a simple, closed, smooth, positive oriented curve. Okay. So this curve bound a region. Okay, we want to integrate over this region. How to describe the region D? What's the best way to describe this region? Grace. What's the best way to describe this region? Sorry? Yeah, so how to describe? What kind of coordinate you want to use? This looks like what? Annular, right? Annular. So what kind of coordinate is suitable for annular shape? You know? Don't know? Okay, let's go to the next one. 永之 how to describe annular object? Sorry, x equals to okay, yeah. So what's that? Can someone help? What's s equal to r cos theta? What's that for? S equals to r cos theta, y equals to r sin theta. What's that? Polar coordinate. Okay, use polar coordinate. So we use radius and angle to describe the points here. Why? Why? Because this region is bounded by 2 circles. okay, bounded by 2 circles, right? So what kind of radius you need to take? Huh? 1 and 2, okay, bounded below by 2, bounded above by, bounded below by 1, bounded above by 2, okay, because the inner circle is 1, outer circle is radius 2, okay. How about the angle? You have to take everything or not? So where, take from where to where? Just from 0 to pi. Okay. So you're going from positive x-axis to pi, okay? And then all the radius in between 1 and 2. Make sense? Does it make sense? Make sense now? Okay. All right. So what does Green's theorem tell you? Okay. So the loop integral of C, okay, of p dx plus q dy is equals to the surface integral d, okay, bounded by C, okay, the region bounded by C, of what? Okay, what's the function you need to do integrate over? You need to differentiate q, okay, in this case 3xy with respect to what? So it is on dy, right? So you need to differentiate with respect to x, okay? Minus differentiate y squared with respect to y, okay, of dn. Okay, so now this one come to the chapter of what chapter is this? Multiple integral. Okay, you want to integrate a function here. So what's this function? This is 3y minus 2y, okay, of dn, which is just y. Okay, so now is the problem of multiple integral. How to do double integral on this function here? Okay, here we got the polar coordinate. Okay, so you need to use the polar integration. Okay, what's the polar integration here? What is the variable you integrate over? R and theta. Okay, dr and theta, and then you need to replace your y with your polar coordinates. Okay, just now, Yongzi say what? We need to substitute x equals to r cos theta and y equals to r sine theta. Okay, so y will become r sine theta. Is this enough or not? No. Why, Pishon? Okay, we need the Jacobian. Okay, we need the Jacobian factor, right? Okay, so we need to multiply the function by r. So where's our range? R is going from 1 to 2. Theta is going from 0 to pi. Okay, and then you do this integral here. So you can split this integral into two parts because the integration domain is constant. Okay, you can split into r part and the degree part. Okay, and then in the end, you will get 14/3. Okay, you can check if you like. Okay. Some calculation I will skip quite quickly because I want to get to a lot of stuff. Okay. Okay, next. Any question on this question here? Example here. Any question on the concept? No. Okay, so let's go on. How about just now it says that Green's theorems apply to simply connected region, right? Because we have a closed curve and I fill in the space. But let's say my space is an annular region. Do you think I can use Green's theorem or not? Do you think we can use Green's theorem on a region that has hole or not? It's not simply connected. Why? Because it's connected. Because it's connected. Because it's connected. You sure? Okay, I'm not sure. But you can use it, okay? So why we can use it? Okay. So I'm not sure we can change the Green's theorem to connected or not, but okay. Let's see about this argument here. Maybe we can extend this argument here. Okay. So how about we have these two closed curve here. Okay, let's see we have these two closed curve here. Okay. One inside, one outside. And then we want to try and integrate over the region bounded by these two closed loop. Okay. So what can we do? Okay. What I want to do is I want to use Green's theorem again. Okay. Green's theorems need a closed curve. Okay. See if we can build two closed curves out of these two curves. Okay. 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 So what should we do? So the first thing I do is let's name some path here. Okay. So let's call the whole path C. Okay, the outer path C and then the inner path W. Okay, with orientation. Okay. So you can notice that W have an opposite orientation with C. Okay, W have opposite orientation with C. Right? Okay. And I further split the C into two parts here. Okay, how do I split? So let's introduce the blue curve here. Okay, the horizontal curve here. Okay, I cut. So basically, what I do is I have two closed paths, and then I cut it with two lines. Okay, any way you could cut it. Maybe you could cut it this way also. Okay. So let's say we pick these two cut lines. Okay. Later the result won't depend on these two lines. Okay. So it's okay. So let's call the positive oriented one B1. Okay, for the left one. The right one we call it B2. Okay. So automatically the other direction I'll call minus B1 and minus B2. Okay. 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 Then I split my C into C1 and C2 as well. Okay. Let's call the upper part C1 and lower part C2, where you can see that C1 is go from the end of B2 to the end of B1. Okay, can you see this? I don't write it precise, but I want you to know what I'm doing. Okay. Similarly, we split W also. So the top part we call it W1, the bottom part we call it W2. Okay, split by the blue line. Split by the blue line. Okay. Okay. In this way, what happened? Okay, what I do is I split my entire D. Okay, let's call this D. Okay, the whole region bounded by two simple closed curve D. I split it into D prime and D prime prime. So you can see that D prime is covered by W, B2, C1, and B1. Okay, and D prime prime is the bottoms, the bottom one. Okay. Yeah, question. Oh, sorry. Bit crazy. So D prime prime. Okay. D prime. Okay. Okay. Yeah. So what am I trying to do here? Okay. I'm trying to split my surface integral into two parts. Okay. Because I've split my D into D prime and D prime prime. Okay. Surface integral is additive. Okay. On on the region that intersect only at the boundary. Okay. So you can see that D prime and D prime prime, they only intersect at the boundary. They don't have overlap. They intersect at the boundary. Okay, the boundary is a line. Right, the boundary is a line. Okay. So I can split my integral from the Green's theorem into two parts. Okay, into two parts. Because this is by the additivity of my surface integral. Okay, I can split integral that only intersect at the boundary. Make sense or not? Does it make sense? Okay. Make sense? I split my integral at the region, only the set at the boundary. If you don't understand what boundary means, you should ask me. Okay? So far, okay or not? Okay. So in this case here, if I split my region into two parts, you can see that these regions are bounded by a closed curve. Bounded by a closed curve. You know what's a closed curve? Bound by a. Okay, so let me ask someone. Can you form a closed curve that bound D prime, Xianmei? Can you tell me what is the closed curve that bounds D prime? What's the curve that go around D prime? C1? C1 only covered this. Does it go around D prime or not? Have it go around D prime? Okay, what else you need? W1, okay, you fill this in. Any more you need to cover D prime? B1 and B2. Okay, good. Okay, so this is the closed curve that bound D1, D prime. Okay, similarly, you will get that C2 minus B1, W2 minus B1 bound D prime prime. Okay, so these are the two closed curves that bound my simply connected region. So I can use Green's theorem twice. Okay, I use Green's theorem to both of these regions here. So I can rewrite this integral here into, let me see here. So I can rewrite this integral here into integration from C1 union B1 union W1 union B2 of P dx plus Q dy, okay, plus integrate from C2 U union with minus B2 union with W2 union with minus B1. P dx plus Q dy. Okay? Okay. So these are line intersect at the boundary again. Okay? So we can split the integral further. Okay, we can split the integral further using the additivity of line integral. So I don't repeat the P ds Q dy, okay? So to save time, I split the integral. Okay, so you should know that there's something inside here. Okay, there's something inside the integral, but to save time, I don't do it. So what do you observe, Waying? What do you observe? What do you observe here? What do you observe? Bunch of integrals. And then that's all. Okay, observe. Let me slide up. What else you observe? Is what? Almost. Some integral is what? Can see or not? So what happened to them? They cancel, okay? Because you take the negative orientation of the positive orientation, right? Okay, so in particular, which one cancel? B1 and negative B1, B2 and negative B2. Okay, they cancel out, right? Okay, so what do you left with? You left with C1, C2, W1, W2, okay? And then you can combine this curve, right? C1 join with C2. And then W1 join with W2. Okay. So actually you are doing a loop integral of these two curves here. Okay. The inner curve and the outer curve at the end. Okay, you understand or not? Understand? So if you do if you do an integration of an annular region, you are actually doing a loop integral for the outer circle and the inner circle with a negative orientation. Right? Negative orientation. Make sense or not? Michelle, any question? Hmm? Which one negative? What is negative? What is negative? I'm asking you, what is negative? You said negative, man, right? Negative is an adjective. I don't know who is negative. So you need to tell me who is negative. What is negative? Did you say negative just now? I mentioned negative. So where is the negative? What? Sorry, I don't get you. What is negative? I mean, where what is negative? I don't know why you're asking. I mean, you need to you formulate your question. I just don't get you. There's nothing wrong about you asking that, but you have to reformulate your question. What is negative? Where did I say negative? Where? You also don't know. So I mean, anything here you don't understand or not first of all. You understand everything? Okay. So a bit hard to communicate like this. If you understand but you got question, but you got question you don't know how to ask. So what's the problem here? Yeah, question. Yeah. Oh, okay. Sure. So what is remember the property we introduced just now? Sorry, I think it's a theorem, right? So how to relate integrate over C and integrate over minus C? What's the relation here? What's the relation? If you change the orientation of the curve, what do you get, Zhexian? I think Zhexian is a pro in this. If you change your orientation of your domain, what do you get? You need to introduce a minus sign. Okay, so integrate over C is equal to negative of integrate minus C. Okay, in other words, integrate over negative direction is the negative of the positive direction. Okay, so what I do is you integrate over minus B2 and integrate over minus B1. Okay, they are negative of each other, and then you add them up, you get 0. So let me write the full things for you. Okay, I think you should do some work, right? You should try and calculate. Sometimes you just sit there and think, right? Usually you can't get it. So by theorem, what is this? This is equal to plus negative of B2. Okay, so they cancel out. Can get it? Yeah. Okay. Yeah. Okay. Yeah. So yeah, I often tell you, right? Mathematics is not just computing. Okay, this is not an arithmetic course. You are not taking a degree of arithmetic. Okay, 算术和数学 is different. Okay, don't just know how to count. Okay, not arithmetic. This is mathematics, not arithmetic. Okay, so you need to think with logic, reasoning. Okay, why we do this. Okay. And then most importantly, you need to communicate. Before communicate, you need to listen. Listen to what people say. Communication. Okay. So what can you observe here? So C is going clockwise, anti-clockwise. Okay. W is going clockwise. Right. Okay. So what you can see, actually you are taking difference of two clockwise loop integral. Okay. So you are taking the difference. Does it make sense or not? It is like you taking the region bounded by outside minus the region bounded by inside. Then you get the annular. Make sense? Does it make sense? Yeah. Okay. Yeah. Okay. So, yeah. So should we proceed with this example or not? Okay, let's do this example and then we take a break. Okay. So let's do this example here. Don't look at this picture first. So let's read the question. So we have this function f. You see, this f is it familiar to you? Minus yi plus xj. What is this? Jimbo, is it familiar? Not familiar? So just now I show a animation for you. Minus y x. What is that? Anti-clockwise rotation vector field. Okay. But this one have an extra stuff. S squared plus y squared. What is that? S squared plus y squared is the distance or the length of your vector. Okay, from the origin. Okay, length of the vector. So at every point, you have this rotation, but you scale by your length. So you only have unique length. Okay, rotation. Okay, good. So now show that this integral, this loop, okay, loop integral, what kind of loop? For any positively oriented simple closed curve, okay, that encloses the origin. Okay, so there's a closed path that encompasses the origin. Okay, it should be smooth as well. So show that you always get 2 pi. Okay, show that you also get 2 pi. But there's a problem here. Okay, there's a problem here. If you want to do closed path that encloses the origin, does this function define on the origin or not? Hmm? Does this function define on the origin or not? How to check? Check it continuous at origin or not, right? So you need to check the limit to 0, 0. Okay, check the limit to 0, 0. So let's check it. Okay, so how to take limit for a vector function? Is how to take limit for a vector function? Components wise. Okay, you take it component wise. Okay, you take it components wise. So you need to do it for the x coordinate and the y coordinate. Okay, so I think this is a revision for your limit section, right? So what's the convenient way to do this? I think the convenient way is to use the technology. What technology I want to use? I want to use polar coordinate, right? Because there's x squared, y squared. So I can use the uh, polar coordinate technology. Okay. So I change my limit to the limit of my radius going to 0. Okay. So what can you see here? What can you see here? What can you see? This limit, what? Why? What happened to the limit? Yeah, what happened to this limit? Infinity. And it diverges. diverges, right? Okay, diverge. Okay, 1 over x diverge. Okay, so this place here diverge. It's divergent. Okay, so in that case, what to do? You already include a point that is divergent. Why the answer is just 2 points? You already have 1 point shift to infinity. And this function should be continuous. Why only 2 pi? Why is it finite? Huh? Again over. Okay, so what we can do, okay, we introduce a smaller circle. Okay, we introduce a smaller circle inside my closed path here to throw away the origin or to remove the origin. And then maybe somehow, after we compute this surface integral, we can look at the limit when the circle going to 0. Right? So we make this circle maybe smaller, 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 and smaller, forever small. And then we look at the limit. What do we get? Okay. Right. So do you get what I'm trying to say? So you have a simple closed curve C, right? It encompasses origin, but origin is a troublemaker. So we put another circle inside my closed path, okay, to remove this origin. And then you can see that if I take this, if I compute the region between these two closed paths here, okay, when I take this circle to infinitely small, then I can approach the whole surface. Does it make sense? Make sense, huh? Okay. Okay. So we will try and fix one circle first and then see what we have. Okay, and then we try and take limit for the radius to go smaller and smaller and smaller. Make sense? This is our strategy now. Yeah. Does everyone get the strategy or not agree with the strategy? You have a better choice. Yeah, you can say, okay? Yeah. Okay. So, so if no one, if you don't say, then that means you agree, then you need to follow. Right. Otherwise, you need to speak up. Okay. Okay. So what do we do? So we introduce smaller circle, smaller circle inside C. Okay, the closed path C. Okay, call it C prime. Call it C prime. Call it C prime. So how to parameterize C prime here? So I parameterize my C prime using A cos t and A sin t. Okay, so I can find some radius. Okay, so that the whole circle lie inside my closed path. Okay, does it make sense? Okay. All right. So my t here is going from where to where? I want to take a full circle, so 0 to 2 pi. Right. Okay. So what do we do? What do we have? What do we have? Okay, what do we have here? So see here, the orientation is a clockwise orientation, anti-clockwise. Okay, anti-clockwise. So, but to apply the result we get just now, we need one of them is anti, and then the inside one is clockwise. Okay, so that means in this case here, what do we have to apply the previous theorem? We have that integrate of C prime, okay, of P dx plus Q dy plus integrate over minus C prime. Okay, because we want the inner one to turn twice. Okay, of P dx plus Q dy is what? Is equals to the surface integral, okay, of partial Q, partial x minus partial P over partial y. Okay. Yeah. Okay, so what is P and Q in our case? Anyone recall? What is P and Q in our case? P is what? Minus y over x squared plus y squared. Q is x over x squared plus y squared. Okay. Okay, so what is partial P over partial y in this case here? It is just y squared minus x squared over x squared plus y squared squared. Okay. How about partial Q partial x? Partial Q partial x. You actually also get x squared minus x squared over x squared plus y squared squared. Okay. You need to compute it. Okay, you need to compute it. Yeah. Right. So you can use quotient rule or you use product rule also can. Okay. Yeah. Okay. So you believe my calculation or not? So easy believe one. Compute, you need to show it yourself. Okay. Yeah, you need to show it. Okay. So I compute that they are the same, so they actually cancel out. Okay. So you get a 0. Okay. So what does this mean? This means that if you integrate over the, oh, this is C, sorry, larger path, okay, is equals to the inner path. Okay. So from this equation here, okay, this sum is equal to 0, right? Okay. So if you move the smaller circle to the right hand side, you get negative. But negative of a negative orientation, you get back the positive. Negative of a integral of a negative orientation, you get the integral of a positive orientation. Oh, I need to write down for you. So minus c plus minus, sorry, integral over c and then plus integral over minus c prime equals 0 implies that integral over c equal to minus integral over minus c prime, which is just integral over c prime. Okay, so I use the negative orientation, integral over negative orientation of the curve. Okay. Okay. Question? Question? Okay. So this is a good thing. Why is it good? C is an arbitrary curve. Okay. But C prime is a circle that we fix. Okay. If it is circle, then we can parameterize it and then calculate it. Okay. So we already parameterize it as what? As a cos t, a sin t. Okay. So this is a line integral, right? So this is a line integral. In particular, this is what? This is equal to integral over c prime of f of dr. Remember? Remember this or not? Okay. So how to compute this? So we already have our parameterization. So we sub our RT in to our force, and then our in our variable become dt. What's the extra thing you need? You need the what? Tangent vector. Okay, you need a tangent vector of your curve. So dot with your tangent vector. Okay. So in our case here, what's our tangent vector here? Okay, what's our tangent vector? A. Hey, you guys don't want to calculate or don't want to speak up? A what? A minus sine t, okay, and A cosine t. Okay, good. Okay, next, so we can substitute our f prime rt in. So what is our f? So it's minus y over x squared plus y squared. So which is minus sine t. Oh, sorry, minus a sine t. Okay, because our curve is with radius a. S squared plus y squared is a squared. And then other side is x, so a cos t, okay, over x squared plus x squared plus y squared, which is a squared. Dot with the dot with tangent vector. What's our tangent vector? Just computed. Minus a sine t, a cos t, okay, dt. So t going from where to where? From 0 to 2 pi. Okay, so we have to compute this whole thing here. So this whole thing will compute to sine square t plus cos square t. Okay, what is this? This is just 1. Okay, integrate over 1, you get 2 pi. Okay, can you see that? This integral here has no relation with the radius. No matter how small you take the radius of an inner circle, it is still 2 pi. Okay, okay. Make sense or not? So if you even if you take limit of a constant number, what do you get? Constant number, okay, 2 pi. 2 pi is the constant number. Okay. Okay. Does it make sense? Any question before I take a break? Question or not? Before I take a break. Yeah, although I have to leave you soon, but I still hope that you can listen to people, okay? Please listen to people. Please listen to people. Everyone in you. Okay, I might not see you in future, but please listen to what people say. Okay. Yeah. Okay, let's take a break until 3:0. Okay, 3:10. Yeah, 3:10. Yeah. 袋鼠干，我可以跟你讲不好吃哦。袋鼠干，
他买了一个袋子给你，
袋鼠干不好吃哦。
他买袋鼠袋给你。
没有，没有。你要问他，他讲了。袋鼠干是什么啊？你知道肉干不是？猪肉干，袋鼠肉干。不好吃。有吃过袋鼠肉？袋鼠肉比那个牛肉更红，所以它更
有点冷，确实。
啊？那边没有肉的，不好吃的，所以我才回来。那边的鸡是快速养成的，所以还没有机会。我的鸡摊没有鸡，它 KFC 不好吃。不过虽然说 KFC 现在马来西亚也变成不是很好吃，啊，
确实不好吃。
不是以前很好吃的，以前很大到很好吃的，但是现在啊，礼拜
看一下，因为我看你表示，我该，所以变成说，我把我的这本来是一个喜了，哦，没，对，D 变成是 D，
嗯，
变成是，
没有，就把一个 annual region split 成两个
一个
simply connected
region。我刚才在想这边我要怎么表示，
什么叫讲表示？
因为你本来的 integral 是，那你看的 integral 是长这样，
对，我只是把这个 C 拆出来写吧，写成一段一段一段一段的。它这个 C 是连在一起嘛，但是它这边也是一段一段一段，只是它有一个容易的解释方法。
是变下来的时候，我把它叫做是，
我本来我这边也可以写成 C 等于 C1 加 C2 加 C3 加 C4。
这个 mobile shape 是几常用的
？Mobile shape 它等一下
到不嘞？
会用到。
我记得
宝宝去。
等一下。哦，什么是 purpose to this ，OK just so what's purpose to doing this?
So I can, because this, I want to compute the line integral of this closed path.
Yeah,
But this closed path involve a origin. So,
that pops up to it.
but by Green's theorem says that this line integral can be related to a line integral of a smaller circle. Yeah. So I can compute this one.
Oh, so just compute this one.
Yeah.
Instead.
Yeah.
So next we compute this one. Oh, 就是不管你这个 region 的长么样，因为它的那个终点它跑去 infinity，你只要切一个在零的，它跑再跑下来的。
再讲一次。
因为你的这个 region，
啊，
你中间有一个跑上去，
对，没有错。
你现在是直接把它抓下来，然后有一个圈的。
我取一个圈，对。
可是那个圈是随便一个，还是你要在那个零？是你，因为你的
没有，肯定是在XY plane 上面嘛。这个图是在 XY plane 上面，这图是在 XY plane。
哦，
对
对，是啊，
呀。那你可能问一个问题，为什么我可以 integrate 这个圈，我不能够 integrate 外面那一个圈？对啊，是不是不能？为什么？但是问题是，他没有告诉你那个圈怎样 parameterize 的。你去哪里找？然后这个结论是对于所有的都是这样。你外面那一圈没有 parameterize。OK， 等一下我去考他们。
如果这个东西里面是 closed 的，就是没有这个，它会有这种情况吗？就是它是 contain origin 的，会有这种情况吗？
听不懂。
就是这个不是因为不能 contain origin。
对，
如果给这个
contain origin 嘛，对不对？对不对？但是我算的是 loop integral，我不是算 surface integral。一开始的时候本来是说我要把它换去 surface integral 来算，但是不能嘛。但所以我要靠一个我能够算的。但是里面这个我有 parameterize，我可以算。外面这个它是说任意的，任意你讲说，你选各种各样的，选不出嘛，对不对？把任意的说成一个你会的。
这个是不是可以跟 n 去
RN？可以，有 RN。等一下我们会有 Stokes theorem。
OK，拜拜。
然后有 Stokes theorem。generalization of Green theorem。circle 我们会 parameterize，你要 introduce 这个 square，只要是 close 的，你要 introduce 这个 triangle 也可以，simple close positive oriented fixed wise 都可以。 你肯定算得出来，你可以试一下，你可以试看，你可以设置方形、三角形、椭圆形都是的，只要你 parameter 得出的形的，你一定要拿，你应该一定会拿。你可以试看，如果你有空的话，你试了告诉我。
16字不够，
也还可以啦，也还可以。我反正会查，只是可能没有这样快回复吧。我会查那个。Hello，everyone here？哎，Y 呢？Y copy disappear。好，快过来。Okay，so how about I ask one question? You see, I integrate over this circle here, right? I integrate over this circle. It also encompasses the origin, right? So why I can do that? Why I don't integrate over the outer thingy? Why don't I integrate straight away integrate the outer part, but I integrate the inner part? The inner circle also contain origin, right? You get my question? You get my question? You okay? Okay, so my problem is, so the outer loop integral is equal to the inner loop integral, correct or not? Just now it says that the outer loop contains the origin, right? So we can't use Green's theorem. But why we can compute the inner loop integral instead? You get my question? Huh? Still no? Huh? No? If think you don't get it, then I think everyone don't get it already. Okay, so what's the result here? So the result here is the outer closed curve, okay, is equal to the integral of the inner closed curve. Right. So just now I said we can't straight away compute the outer closed curve. But now we compute the inner closed curve. But inner closed curve also contain origin, right? Okay. So what's the problem here? Why? Do you know why? No. Okay. Because this integral here need to check for all possible simple closed curve. So if I give you any closed curve, do you know how to parameterize or not? How to parameterize it? Any possibility of, right? Okay. So what this question do is you reduce the case of any possibility to one possibility, which is just a circle. Okay or not? Okay, this question turns to the question to check everything to just check one thing. This is a frequent technique used in a mathematical proof. Okay, you want to check on a lot of things, but you reduce the question to just checking one thing is enough. And then the thing is easy to check. Okay, this is the frequent use in mathematics. Okay, we reduce a hard question to an easy question. Okay, make sense? Make sense? Yeah, question.
So this vector field.
This result is only valid for this vector field. Yeah, because when you compute the integral, right, it depends on what vector field you put. Right, the computation depends on the vector field. If you change different vector field, then you compute different integral. Yeah, so it depends. Correct. Yeah. Makes sense or not? This force is rotational. Okay, 2 pi. Okay, it's 2 pi. Sorry, what am I saying? Okay, so this force field, vector force field, is rotational. Okay, so if you rotate one round, is 2 pi r. Okay, maybe 2 pi r. But the calculation tells you that no matter what closed curve you take, your work done is always 2 pi. Okay, you move in a large radius, move in a small radius, you will also get 2 pi as your work done. So work done is the same no matter what radius you move in this rotational vector field. Okay, now you see the result telling you. Okay, because this is true for any single closed curve. Okay, irregular one also can, as long as it is close, enclosing the origin. Irregular one, you move around this origin, you also get 2 pi. No matter how big, how small, how irregular is it, you always get 2 pi. It's the same. Okay, it might seem that you move a lot, but in the end, your work done is still the same. Okay. Yeah, I mean, this is the physics stuff, not mathematics. But, okay. Okay, so just now we say that del P del Y, okay, del P del Y, del P del Q del X, right, is coming from a cross product. Okay, so let's see how does it come from a cross product here. So we first define curve. Okay, curve is a cross product. Cross product, you need two materials, right? You need two vectors. So vector field give you a vector. What vector you need to consider? You need to consider this gradient operator here. Okay, del over del x, del over del y, and del over del z. Okay, this vector operators here. So if you like, I also can rewrite this is in a row vector form. Okay, row vector form. Okay, so we define curl as a cross product. See if this gives the right hand side of the Green's theorem or not. Okay, so we define it more generally. We define it on F1, F2, F3, so 3-dimensional. Okay, and in fact, you can extend it. Okay, but in our course, we just do until R3 because we only can draw until R3. So if the first partial derivative of our vector field exists, then the curl is defined as a cross product of the gradient operator with our vector field. So do you know this notation here? Determinant of this matrix. Okay, so you regard the thing inside as a matrix and then you take the determinant. Okay, so how to do determinant of a matrix? How to compute a determinant of a 3x3 matrix? Choose the direction first. Okay, what's the method called? Cofactor expansion. Okay, cofactor expansion. Okay, choose a direction. Which direction we want to choose? Okay, choose the first row. Okay, we choose first row. So remember that in cofactor expansion, you have a plus minus plus contribution. Okay, so first, if you have plus at the I part, so you take the minor, okay, minor of I. So you multiply del y on fx f3 and then del over del z on f2, okay, and then minus ab minus ad minus bc. Okay, good. AD minus BC, okay? AD minus BC. So you got this part for I. And then for J, you get del F3 over del X and del minus del F1 over del Z, okay? But you can see that, why this swap position? Why swap? Ryan, why swap? Because we got a minus from our cofactor expansion here, okay? So swap position. And then for K, you check the minor also, okay, which is del of del f2 over del x minus del fy over del y, del f1 over del y. Okay, so this is how you do the cross product. So how is it related to our case just now? Our case just now has what? Our case just now only have two variable, not two variable, but two component. Okay, our component is F1 and F2. Okay, so you regard the F3 as zero. Okay, we regard S3 as zero. So we reduce the okay, let us call this G so that you don't confuse why so many F here. So I replace our example just now with G. So what is the curl of G? Okay, what is the curl of G? Del X, del over del Y, del over del Z, G1, G2, and 0. Okay, so what's this cross product here? Import. What's the cross product here? Negative G2. Huh? Del G2 over del Z. And I like this. Anything else? Plus del G1 over del Z. J plus del X. Okay. Anything else? Bracket. That's all. That's all. Okay. Let me have some other to check. Chiron check. Is it correct or not? So you have I, you check this minor here. Okay. Okay. I think I know what's going on here. Okay. So, okay. I think I know what's going wrong here. So the del we're taking here, right? I think we should just restrict to two variable. Okay, we just restrict to two variable because there's no change in the z direction. So we should restrict this to 0. Okay. So then these two terms will disappear. Okay, so we remove these two. So we only left with this two. Okay. Okay. So this is the exactly the coefficient of the k here. Okay, is exactly the Green's theorem part. Okay, del of G2 over X, del of G1 over Y. Okay, but the difference here is I have a unit vector here. Okay, I have a unit vector here. How to get rid of a unit vector? Okay, so later we will introduce what the surface integral is. Then we can remove this unit vector. Okay, yeah. All right. So this is called a curve. Okay. So why we call this a curve? This is exactly motivated by the Green's theorem, right? Because Green's theorems, the left hand side tell you what's the work done in the circular motion, right? A loop, circular motion. This is why we call this operator here a curve. Okay. It's not I have curve first and then I got this. It's because I see the phenomenon and then I define this. Okay, this is typically what we do in mathematics. Okay, yeah. We try to see what's the property it holds and then we give it a name. Okay, so this is a curve of a vector field. All right, so shall we, you want to do an example of finding curve or not? Or you are okay with this dot product? You want to do example? You want to try and do skip? Skip or do? Wait, I mean decide, don't laugh. Skip. Okay, one says skip. So everyone agree. Okay, we skip this. Okay, good. So let's skip this. So the next theorem is curl of a gradient of f is 0. Okay, curl of a gradient of f is 0. Okay, so we just try and compute this. Okay, curl of a gradient is 0. So let's compute this quickly. Okay, what's the gradient? Okay, curl is the curl operation. Okay, so this is the curl operation. What's the gradient of f? Last time I think I asked someone, forget who already. 原加. What's the gradient of f? What's the gradient of f? F? Sorry? What's the gradient of f? F1. F? You have so short. F1. Fx. Okay, f differentiate with respect to x. And then? Hey, why is it so hard to speak up? Yo, I don't know. Already so grow up 20 years already. Don't know how to speak out. Second one is del f over del y. Okay. Third one is del f over del z. Okay. What I want to say is I think there's nothing to shame about. Okay. To speak up. I'm not asking you to what do bad things, right? Okay. Just answering question. That's all. I'm not sure why it's so hard for you. Maybe no teacher push you like this. I'm not sure. Yeah. Okay. So how to compute this? Next, the first term you have del square f del y del z minus del square f over del z del y, and then minus del square f over del x del z plus del square f over del z del x, and then del square f over del x del y minus del square f over del y del x. Okay. So, what happened to this term? Okay. Can you see that these are all mixed partial derivative? So these are all mixed partial derivative. So they agree by Claira's theorem. Okay. So differential with respect to z is equal to differential with respect to y, and then differential with respect to y is equal. Differential with respect to z, and then differential with respect to y is equal to differential with respect to y first, and then this differential with respect to z. So if you change the order, they are still the same. But of course, they need to satisfy some condition here. But those conditions should be included in this problem here. Okay, because we want to able to compute the partial derivative of f. So they are included in the condition, okay, of the theorem. So actually, they all cancel out by Claira's theorem. Okay, Claira's theorem. Okay, so what does this mean? Okay, what does this mean? Why we care about del f? What things is equals to del f? What is del f? Del f is a vector field. What kind of vector field? Huh? Just now we recall this definition. A vector field is conservative if it is equal to some gradient of f. So gradient of f is a conservative vector field. So that means that If you take a curl of a conservative vector field, you get 0. Make sense or not? Okay. If you take a curl of a conservative vector field, you get 0. Okay. In other words, how to check a vector field is not conservative? Sorry? Check that whether it is 0 or not. If it is not 0, then the curve then it is not conservative. Okay. But does it imply the other way or not? Is the other way automatic? If the curl of a vector field is 0, then it is conservative. Is it automatic or not? Is it automatic by this theorem? Yeah. Automatic is like is the direction is the other direction implied by this theorem? Does it imply by this theorem or not? Huh? So what's this theorem in other words? So this theorem says that if f is conservative, okay, that is f equals to some del f, then curl of f is 0. Okay, curl of f is 0. Okay, curl of f is 0. So the contra positive of this statement is if the curl is not 0, then f is not conservative. So does this imply that if curl f is 0, then f is conservative? No, right? Okay, no. Okay, it doesn't, because P implies Q is not logically equivalent to Q implies P. Okay, but recall that what theorem we have last time. Okay, do you remember that we need to check some weird tree equation to check that F is conservative? Let me recall this. Do you recall this definition here? Okay, so what are these three equations here? Are these partial derivative looks familiar or not? What are these 6 terms here? What are these 6 terms here? This is the curl component. Okay, the curl component of your vector field. Okay, let me remind you what is the curl component here. Okay, how about I move this down then? So let's move this down. So last time we didn't prove this statement, right? So we just use this. Okay, so let me move here. So I copy here. Okay, and then I also bring my curl definition down. So let's move this part here. Okay, then I do this. Hey, although I didn't do this exercise in class, right? Make sure you need to do hands-on at home. Okay, because mathematics is like this. Sometimes you think you understand, but ask you to do hands-on, you cannot do one. Okay, so you need to practice both. So mathematics is not about theory. You have to do it practically. Okay. Yeah. You have to do have to improve in theory, improve in practical, both skill you need. Okay, let me take it here. Okay, so you can see that if I set my curl equal to 0, okay, the first component is what? Is the third equation here. Okay, if I set the first coordinate to be 0, is my third equation here. If I set the second coordinate to be 0, is the second equation here. And then if I set the third component to be 0, then this is my first equation. Okay, so these 3 equations here actually coming from setting the curl to be 0. Okay, so you can see that this theorem here has extra condition. You want your f defined on an open simply connected domain, and also f1, f2, f3 has to be continuous. Okay, so there's some extra condition if you want to go from the direction that curl is 0, then f is conservative. Okay, yeah. So actually you have both way, but one way have some extra condition. Any question? Okay. 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 So there's some picture here telling you what's the curve. So if there's the curve is non-zero, that means it is rotating around the origin, a point. Okay, for example, if it is zero, then it is not rotating. Okay, it just go. Okay. Yeah. So there's a summary here. Okay, there's a summary here. Okay, where's the, what time is it? 3:34. Okay, maybe let's do one example to strengthen your memory here. Okay. So determine whether this vector field is conservative or not. Okay, determine whether this vector field is conservative or not. So what should you do? What should you do? Shifong, what should you do? What's the definition of vector field being conservative? Per S is equal to 0. Okay, then imply the vector field is conservative. Okay, but you need to have extra condition, right? Check in the, so you need to have here. So you need to check it is defined on open simply connected and then domain, and then the component function has continuous partial derivative. Okay. So if it's zero, then it is conservative. It is non-zero, then it is not conservative. Okay. What's the definition of being conservative again? The vector field is equal to what? A definition is very important. Definition is very important. Sometimes you don't need to use extra technology. You just prove from definition. Okay, definition is always important one. So what's vector field being conservative? Yeah, it is a gradient of a scalar function. Okay, we repeat it, repeat it, and repeat it again and again and again, again and again. Okay, so must remember. So if you straight away found the scalar field, then you are done. Okay, otherwise you can use the curve technique. Okay, so you check the curve. So let's check the curve. So what's the curve of the function? Or of this function here? Okay, so you build your matrix. Okay, and then take the determinant. Build your matrix and take the determinant, which is the cross product between the gradient operator and the vector field. Okay, so in the end, what do you get? So you get 2x, 2y minus 2xy, 0 plus x of yz minus 0. And you can see that this curve here is not 0 for all the points. Okay, so this is non-zero. Okay, if it is non-zero, that means this vector field is not conservative. Okay, so this is not a conservative vector field. This is not a conservative vector field. Okay. Yeah. So should we resume speaking about the exact stuff? Okay, so I think we have enough tool to speak about this exact stuff. So what's the definition of an exact differential equation? What's the definition? So this one provided by Jiang Chen one. Okay, Jiang Chen is the first one who replied me. But he cannot come today. Maybe he can say hi if you want. Okay, so you start with this mdx and dy. Reminiscing or not? pdx q dy. Right, just now we deal with this. But now you set it as 0. Okay, you have some extra condition. You said that, hey, this function must be 0. Okay, set it to be 0. And then you say that there exists an implicit function solution of the equation fxyc if and only if the following holds. What is this? This term is appearing in our Green's theorem. Okay, this term is appearing in the Green's theorem. All right, so they are equal. What does it mean? The curl is curl is 0. Okay, the curl is 0. If the curl is 0, what does it mean? This is how we say. If you check that the curl of a vector field is 0, what happened to the vector field? Thingy. If a curl of a vector field is 0, then the vector field is conservative. Okay, the field, so in particular, if the vector field is conservative, what does it mean? It is the gradient of some scalar field. Okay, gradient of some scalar field. So how do you find your solution here? Okay, you look at your own textbook. Everyone got this textbook, right? Okay, I think when I study, I also use this textbook. Okay, but older version one. So how do you solve it? You found a function. Okay, you found a function such that if you differentiate with respect to x, you get m. You differentiate with respect to y, you get n. Okay, this is a gradient of v here. Gradient of v. Okay or not? Okay. So the scalar field solve your problem. Yeah, solve your ODE here. Does it make sense? Means you a bit blur. The question or not? Okay, I explain this is basing on you understand the context in your ODE. If you don't understand the context of ODE, then maybe I have to explain more. Okay, any question or not? My punchline here is the solution to your exact equation is exactly the scalar field. Okay, this is my punchline. Okay, so what is this? You see, suppose that we can identify a function. Suppose that. So where did suppose come from? Out of nowhere one. Okay. So I tell you where. That's a scalar field to this m and n. Okay. This m and n is a gradient of that scalar field. Okay. Okay or not? So when you read mathematical text, right? Okay, sometimes they will say, suppose okay, something happened out of nowhere one. You just have to believe. Okay. So sometimes when we relate different area, then we'll see, oh, this thing's kind of natural because from here is natural. Okay. From the other side, it's like, oh, no. But from one side, it's natural. Okay. Can get the idea or not? Okay. Yeah, nothing much to share here. I mean, yeah. But yeah, the punchline is the solution is when the vector field. So the vector, your m, your OD start with an m and n here. So what's the m and n here about? Is a gradient of some scalar field. Okay, gradient of some scalar field. Okay. Also, I tell you another thing. Okay, another thing. Okay, Ming Xiu said this topic a bit dry, right? Okay, let you think more again. So remember how we prove that f is conservative? What's the three condition? Remember, the path integral of a conservative vector field is independent of path. Remember, independent of path. Okay, and then integrate over any closed loop, you get what's the value you get? You must remember. Thinking. What's the value you get if you integrate a loop on the vector field? A vector field on the loop. What's the value you always get? Remember? Maybe guess a number. Try and guess a number. Just guess one. Sorry? Can you give me a number? Just give me a number. Hello, Lin Jing. Hello. Can you give me a number? Number or give me a number. Please give me a number. One number is enough. Any number. Okay. Next. About Liu Qing. Liu Qing. Do you know what's the closed loop interval on the conservative vector field give? You know? No. Can you give a number? Give a number, please. Sorry. Give a number. Give one. Let's show me. Huh? Give one. Cannot. Give one. This one. Anyone. Anyone. Okay. Next. Who is beside Liu Qing? Who is beside Liu Qing? Inqi. Inqi. Can you give one number? Give me one number. Cannot give one number. Wow, your English is so good. I saw your project. Can you give me one number? I mean, give one number. Also don't know. It is so hard to give one number. How about Xie Yan? Xie Yan. You know what's the closed loop interval of a vector conservative vector field? Okay, you want to give me a number? Okay, can give me one. 5. Okay, not 5. Sorry. Okay. How about Xie Mei? You don't know. You want to guess or not? 15. No. Too random are the number. Number a bit random. Okay. How about Sun Ling? You know? Don't know. How about guess the number? 0. Yeah, 0. Okay. Integrate over a closed, okay, of a conservative vector field, you always get 0. Okay. So what is this? You see, you integrate this function with respect to closed loop. Right. You integrate the left-hand side of a closed loop. What do you get? You're integrating over 0 function. You always get 0. Okay. So meaning this is coming from a conservative vector field. Okay. Yeah. Okay. So let's go back. Okay, 0. I mean, certain in mathematics, right? Certain number have meaning one. Like 0, 1, minus 1, something like that. Or you will think you will heard people saying, I think 23 or something like that. Some number are quite special. Okay, so take note of those numbers because nature likes those numbers. Yeah. What do you mean? How many number is special? Quite a lot. Yeah. Yeah. Maybe next time we will see. 520, huh? Okay, yeah, special, very special. Special for your Valentine. Yeah, thank you. Okay, next. So okay, we will skip this conservative example so you can try it out. So if you see, last time we have solved this kind of problem already. Actually, it's similar in ODE. You integrate over the partial derivative and then you differentiate and then you check the equality and so on. Okay, so on and so forth. Do you know what am I talking about? You know? Okay, yeah. Okay, sure, good. Okay, next, divergence. Okay, so between the gradient operator and vector field operator, you take cross product. Okay, similarly, you can take dot product. Okay, if you take dot product, we call it a divergence. Okay, later when we introduce divergence theorem, you will see why we will call this thing a divergence. Okay, so divergence is a dot product between gradient operators and vector field. Okay, so you do this. So how about we do this example? I think it's real quick. So if I want to do diff of a vector field, so what do? I take the dot product between gradient vector and vector field. So let's write down all the vector we need. Okay. So I differentiate with respect to x squared yz plus del over del y of 3x yz cubed plus del over del z x squared minus x squared. Okay, so what's this? Okay, so you just differentiate components by component. Okay, and then you will get the diff. So this diff here depend on points. Okay, at each point you have different value. Okay, at each point you have different value. In particular, if you see that the diff, okay, the diff is less than 0, what does it mean? It means that it is converging to the point. Okay, if the diff is greater than 0, that means it is diverging from the point. Okay, how about 0? It means that there are flow that going in and out. Okay, in and out. So you see, in and out, in and out. Okay. So in particular, for the first one, we will call it a sink. Okay, sink. So it's like a water sink, right? All the water flow into it. And then how about this? Flow out. Huh? King. King. Okay. Okay, sure. How about another word? Better word. Better word. Yeah, sauce. Hey, who says sauce? Yeah. Who says sauce? Who? Eating? Eating. Who says sauce? Oh, means you, Okay, yeah, sauce. Okay. So you are sauce. Okay, you give out things. Okay, you are a sauce. You give out things. Okay. So the third one, you have flows that going in and out. Okay. So one is sauce, one is sink. I don't know. Maybe I don't check. Maybe got name. Okay, sure. No, I'm a sauce. I'm a sauce. Okay. Not tomato sauce. Huh? I said not tomato sauce already. Okay. Chili sauce, yeah. Okay. Sure. So any question up to curl and divergence? Any question up to curl and divergence? Check conservative Green's theorem. Yeah. Okay. You mean this V? You mean the V here? What? Oh, okay. Sorry. Yeah. Sure. Yeah. Sure. Okay. Thank you. Okay. Okay. Let's take another break until 4 o'clock, and then we will resume with surfaces. Vector here, right? Vector. Sun here. 诗瑜、顺明、凯伦、金波、齐峰、华英、李双、英喜、何怡、雪岩、江城 Sink、嘉业、here 李凯、袁家、文硕、丁、玉维、边博、本业、林金、董洁、玉金、一 宜州 here or not 宜州 ？OK，定语柳晴、真诚、若宁、鼓励、严谨 here，子倩、泽轩、莹莹、Grace、沙叶、嘉文、明秀、Michelle、Brian、Ellie、永志、雪梅。是吧？嗯，gradient 是多少？gradient，它这个不是 surface，它这个是一个 vector field。这个 vector field 是说一个点上面我有 gradient of 一个 vector field 没有 define 过，没有 define 这个东西。gradient of vector field 就是一个方程。什么时候 vector field 是个 gradient？这小事啊。vector field 这个方程对，它不一定是 gradient of 一个 gradient of vector field 就是 gradient。gradient of 一个 vector function，vector OK 也不是，给我等一下，gradient of 一个 function，我们只 define 过 function 啊，没有 define 过 I T I N 这个 function，没有，我们没有 define 过 gradient 两个 function I T I N，我们的 gradient 是 define 我们 I T R 的 function。I N 的 所以它的 gradient。
然后这个因为它也是 cos，然后它不等于零，代表说它不是孔子边界，
Yes，
因为它不可能它那个
就是
因为
那个
因为你发现啊，它的del FE over del 不一样
啊
，del FE over del S，del FE over del Y 就是 del F2 over del。
OK OK，你
它
那个意思，yeah，你那个，OK OK，是
这样就有意思。
是可以，good point，good 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 point，对，非常好，等一下我再讲一下。
exactly 看你画
嗯哼，
那个 relation 的时候，这个就是你的那个一个 component，这是第二个 component，
P 跟 Q，
然后这个其实就是第二个 component I，这个 component 我 J，
sure，可以，没问题。所以你要把那个想成一个 F 哦。对
然后 express in the one form，
，express in the one form。
是这个
Yeah， correct，非常好，我觉得很好。All right， very good. Yeah, I think very good. Okay, what's the good thing here? So just now actually, Siyu reminded us this computation here. You see, this is equal, right? Okay, del f1 of del y and del f2 of del x are equal. Curl is 0. Curl is 0. But the loop integral is not 0. What's wrong? What's wrong? Qifeng, what's wrong? Qifeng, what's wrong? Curl is 0, but the loop integral is not 0. Just now, curl 0 implies what? F is vector field is conservative. If it is conservative, then any closed loop integral is 0. Okay, but you get 2 pi here, not 0. What happened? What happened? What happened? Mathematics go wrong already. What happened? What happened? See this statement here? You not only want the curl to be 0, you want the partial derivative to be continuous. Okay? But the partial derivative just now is not continuous at the origin. Okay, this thing is not continuous at the origin. Okay? So you see, a single condition you cannot throw away in the mathematics theorem. If you throw away, then you will be wrong. Okay, not a single condition you can throw away inside the theorem. Okay, every condition is equally important. Okay, every condition, every single condition in the theorem is equally important. Okay, yeah, why? You lost the most interesting part. We just finished. Okay, nothing. We just say that if the curl is 0, but the partial derivative is not continuous, then f might not be continuous, conservative. Okay. Okay. There's one more thing I want to say. Okay, there's one more thing. Okay, this is extra stuff. If you don't understand, it's okay. But if you understand, then I hope you can pursue in this direction. Okay, so you can see curl on gradient on f is 0. Okay, so there are two operators acting on f. Del and curl. Okay, del and curl. Okay, you input of f. Okay, so sometimes, right? Sometimes we will write it in some form like this. So we have a, let's say f live in some function space. Okay, let's call it O1. Alright, let's call it O1. O1. So I can send f in O1 to del f, maybe call it L2, O2. Okay, and then send it to curl of del f in a space called O3. Okay, these all I call it some function space. And then these are the map that send my function. Okay, so one map going from O2, O1 and O2 is delta, and then the other map is called curl. Okay, and then the composite of these two map is 0. Okay, so this is some extra thing. If you don't understand, it's okay. If you just want to listen it as a story, fairy tale also can. Okay, but if you think that this one is going to your heart, then please continue in this direction. Okay, so if you compose these two functions, okay, curl and del on f is 0. Sometimes we call this the whole thing we call a chain complex. Okay, map between different function, and then the composite of the function, two function, continuous function, not continuous, composing two adjacent function is 0. Okay, we call it a chain complex. Okay, then yeah, we can learn a lot of stuff. So these stuff, so what you learn here is included in the topic called exterior derivative. Okay. If you go further in the direction of geometry, you will see this. Okay, these are extra stuff. Okay, if you don't understand, it's okay. Okay, but in future, if you see exterior derivative, you should come back and think about this curl, divergence, and then gradient. Okay, if you met the word exterior derivative and also differential form. Okay. Yeah. Okay, so let's forget about this. This is a dream, so forget about this. Okay, next. So the idea is in line integral. Okay, what we do is we study the line in R3. Okay, we study the line in R3. So every point have 3 coordinates. Okay, every point has 3 coordinates. So we introduce a technology that is to parameterize the curve. Okay, we parameterize the curve. Or we parameterize curve using T. Okay, one direction. We use one direction to control 3 directions. Okay, on the curve. So this is a parameterized curve. But now we want to upgrade this construction. Okay, we want to generalize this to 2-dimensional surface. Okay, let's say we have a general surface. Okay, how many variables do we need to parameterize it? If I have a surface, okay, how many variables do I need? 3 is a bit too much. Okay, 3 you can go in 3 directions already. So you build a solid. Okay, so if you just want to move on the surface, you just need 2 directions. Okay, you just need 2 directions because you can take the linear combination of these 2 directions. Okay, you can take the linear combination of these 2 directions. Then you'll get a surface. Okay, so this is what we call a parameterized surface. Okay, so this is what we call a parameterized surface. So what you should think is, I got a line. Okay, I got a real line. How does real line fit in R3? Yeah, how does real line sit in R3 for curve? For surface, how does R2 sit in R3? Okay, how does R2 sit in R3? Okay, how does R2 sit in R3? So you need 2 variables. Okay, let's call it U and V. Why I call it U and V, not X and Y? Because we take X and Y as a regular coordinate. U and V can be anything. Okay, so this is the why we choose a different convention here. Okay, X and Y we reserve for the usual coordinate here. So X, Y, Z, again X, Y, and Z. Okay. Okay, so let's see. So how to parameterize surface? Okay, so this is the vector function. I hope you still remember what is vector function. Function that is outputting a vector. Okay, vector function. So why this vector function have 3 coordinates here? So, sorry. Because our surface is living in R3. Okay, you need to tell me what's the X direction, Y direction, and the height. Okay, then I will build the surface for you in R3. Okay. Line also the same, right? We have ST, YT, and ZT because it is living in R3. Okay. So so this is a parameterized surface, and then next. Okay, next is this. Okay. Can you recognize what is this parameterized vector function here? 2 cos u, okay, in the x direction, b in the y direction, 2 sine u in the z direction. Okay, what is this? Huh? Sorry, cylinder. Okay, why? Can you see that this x and z here satisfy a circle equation? Okay, because they are both in terms of u. Okay, they satisfy an equation called 2 cos u squared plus 2 sine u squared equals to what? 总结。4. Okay, so the radius is, what's the radius of the circle here? Two. Okay, good. It's the square root of 4. So it's 2. Okay. So this is in which direction? X and Z. Okay, XZ plane. You got circle. But on Y, it's a different variable. Okay, so you can have anything on the Y. So you have the infinitely long cylinder. Okay. Make sense? Why don't play phone? Okay, good. Yeah, good, very good. Don't have computer? Rosa again. Buy new one. Okay, good. You got money, right? You got money, right? Don't buy too much coffee. Don't buy too much juice. Okay. Next, so you have this surface. Okay, how about plane? How to parameterize plane? Okay, how to parameterize plane? How to build a plane? How to build a plane? Do you remember or not? How to build a plane? How to build a plane? Two linearly independent vectors. Okay, you need two linearly independent vectors. If it is dependent, how? You just get a line, right? One have to be scalar of one another. So you need two linearly independent vector here. Okay, let's say we have these two linearly independent vector. Call it B1 and B2. Sorry, A and B. Okay, and then we name B. So let's give some coordinate to this vector here. B1, B2, B3, and A2, A3. Okay. So on your plane, it should contain some point, right? Okay, it should contain some point. Let's fix a point. Call it P0, P0. Okay, call it a point. S0, Y0, and Z0. Okay. So how to describe the points on this point, on this plane? Okay. Every point on the plane should be a linear combination of the two vector A and B. Okay, right? So let's call this arbitrary P on my plane, on the plane. Okay. So we can write it as so the vector here can be written as a linear combination of the two vector A and B. Okay. So in general, what? In general, this surface here can be described as UV. Okay. UV with the linear combination of the two linearly independent vector. Okay. Is this enough or not? Okay, so I already got all the linear combination of these two vectors. But is this enough? Enough. Do I have P0 on this plane or not? Do I have P0 on this plane? Not sure. Okay, not sure. But the easiest way to make P0 on this plane is what? You just add the point into your plane. Okay, the easiest way is to do this. Okay, why when I add this point here, it appeared in my plane? Why? Because when I sub u equals 0, v equals 0, it's solved to the fixed point on the plane. Okay. 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 Yeah. So this is a vector function. Okay. How to write it as a parametric equation? Still remember what parametric equation means? You need to give me all the equation for the different parameter. Okay. X is what, Y is what, Z is what. Okay. So in this case here, what is my X? What is my X in this parametric surface? Given you already the vector function. Can you find what is X coordinate? How to read the X coordinate from the vector function? A1. A1 is X, Y, or Z? A1 is X, A2 is Y, A3 is Z. Okay, so now I only want X component. So how to read out the X component? U times A1 plus B times B1 plus S0. Okay, good. Then similarly for A2, you get AU plus A2 plus V times B2 plus Y0. U plus A3 plus V times B3 plus Z0 for Z. Okay. Yeah. So these are two functions that you need to go forward and backward. Okay. You need to know how to go from parametric equation to vector field, and then go from vector equation to parametric equation. Okay. Okay. Last one we try. So let's say you're given a sphere with radius A. Okay. How to parameterize it? Any idea? How to parameterize a sphere with constant radius? Means still, how to parameterize a sphere? So what kind of coordinate you are using? Okay, you are using a spherical coordinate. But spherical coordinate have how many variables? 3. But this surface here only have 2. So how? Cylindrical also have 3. Right, 3 variables. Okay, spherical have 3 variables. What are the variables? Radius, the angle from the positive axis, and then the angle from the positive z-axis. Okay, phi and theta. So these 3 variables here. Okay. So any method to get only 2 variables? Fix one. Why can we fix it? Fix which one? Not sure. So this is a sphere with radius what? Radius A. Okay. Radius is already being fixed. Okay, you just need theta and phi. Right. Okay. So turn it to a spherical coordinate. Spherical coordinate. We have x equals to a sine phi cos theta, y equals to a sine phi sine theta, and z equals to a cos theta. Sorry, phi. Okay, so phi is going from where to where? From 0 to pi, and then theta is going from 0 to 2 pi. Okay, or you can write it as a vector field function form. Okay, so you just write everything in a row vector form. Okay, row vector form. Row vector form. Okay, so the technique of writing parametric surface is very important, because later we're gonna do surface integral. You need to know how to parameterize your surface, because similar in line integral. Okay, you need to know how to parameterize your line. Horizontal line, how to parameterize. Semicircle, how to parameterize. Okay. Similarly, now I give you a surface. Okay, I give you a sphere. I give you a cylinder. Okay, how to parameterize? Okay, so you need to learn this. All right. Okay, so let's skip this. Okay, similar to the tangent vector, right? Tangent vector of a line. Now we need to find the tangent plane. Okay, how to find the tangent plane? This is just 2 chapters ago. Okay, how to find the tangent plane given you a surface? You need to compute the 2 directional derivative. Okay, so in this case, last time we used xy, right? So you need to find fx and y. But this time we use uv. So you need to find ru and rv. Okay, you need to differentiate with respect to u and then differentiate with respect to v. Okay, so you get the tangent vector in the direction of u and in the direction of v. Okay, so from these 2 tangent vector, you can find the tangent plane. Okay, at every point. How to find the tangent plane? You just take the linear combination. Okay. So RV is partial differentiate every component. Okay, with respect to V. RU is partial differentiate with respect to U at every component. Okay. So RV and RU, right, is a tangent vector. So when you cross them together, still remember what do you get? What do you get? When you cross 2 tangent vectors together. Hey, cross product. A vector. What vector is that? Perpendicular. A normal vector. Normal vector to what? Where does the tangent vector live in? Live in what? R3 space? Okay, sure. What plane does it live on? Tangent vector live on tangent plane. Yeah. So the normal vector is a normal vector to the tangent plane. Okay, good. So if you check that this cross product here, okay, the normal vector is non-zero, then it's always non-zero, then the surface is smooth. Okay, it's differentiable. Okay, it has no corners. So the tangent plane, remember, I recall, the tangent plane at the point is the plane that contains the tangent vector of any curve. Okay, any curve passing through that point. Okay, and then the cross product of 2 tangent vector is the normal vector to the tangent plane. Okay, can you remember revision? Okay. Last time we only do on xy. Okay, but this time is more general. Any UV. Okay, not linearly independent UV. Okay. So I want to maybe highlight how to find RV, how to find RU. Okay. And then what is tangent plane? Okay. And then what is RU close RV? Okay. All these things is very important. And these are the important things. And you start with a parameterized surface. Okay, let's do one example to strengthen your memory. So find the equation of tangent plane to the following surface here. Okay, this is a surface. And then I want to find tangent plane at a point 113. Okay. The procedure to find tangent plane is what? You need to get the 2 directional derivative. Is it directional derivative? Fx, Fy. Yeah. Okay. Yeah. So we need to compute Ru and Rv. Okay. What is Ru in this case? 2U, 0 and 1. Okay. Rv is what? 0, 2v and 2. Okay. So to get the tangent plane, right, you need to take the normal. You can take the normal vector. Okay. Either you use this, either you use the normal vector. Okay. Let's use the normal vector. So what's this cross product here? you get. What's the normal vector here? Minus 2v minus 4u 4uv. Okay. So which point we want to check? We want to check at the point 113. Okay, 113. So but our variable here only u and v, right? So how to obtain u and v? How to obtain u and v? How to obtain u and v? Okay, so you get the three equation out from your vector function. Okay, so what are the three equations? So in the first coordinate you should get 1, second coordinate you should get 1, and the third coordinate you should get 3. Okay, so let's analyze these three equations here. Okay, u squared equals to 1, v squared equals to 1, meaning u and v must be plus minus 1. Okay, plus or minus 1. But how to satisfy the third equation here? How to get 3? Only u equals to 1, v equals to 1 can get 3. Okay, if you try all the other possibility, you won't get 3. So this implies that u equals to v equals to 1. So let's check what's the normal vector at 113. So at 113, we get minus 2, minus 4, 4. Okay, so if this is 113, we get a normal vector pointing minus 2, minus 4, 4. Okay, minus 2, minus 4, 4. Right? Okay, so you got a normal vector. Okay, you got a point. How to build a plane equation? What's the equation of plane? Forgot? Forgot? Who remember? Equation of plane. You remember or not? Equation of plane. Equation of plane. With normal vector ABC. Let's say ABC. So what's the equation of plane? Something equals 0. So what thing equals 0? How to build a plane using normal vector? At the point, maybe at the point x0, y0, z0. Okay, so these 3 numbers here, how to build a plane? 6 numbers, right? What's the plane equation? A times x minus x0 plus, and then plus c times z minus z0. Okay, so you plug everything in, we already got our normal vector. Okay, and then we also got our point 1, 1, 3. 1, 3, right? Yeah. Okay, so this is the plane equation. Okay, so you can see here. Okay, I finished done with this part. What I want you to see is if I put negative everywhere, right? The same point satisfy the equation. Okay, so what's the difference of if I put an extra negative? What's the difference? The normal vector go to the other direction. Okay, so in nature, you have two choices to choose this normal vector for a plane. Either you can choose up or either you can choose down. Right? They are on the same line. Okay, but they give two directions. Okay, so these are the two possible directions we can. Okay, so later we'll come back with these two directions we can put on the surface. Okay, make sense? Does it make sense? Okay. Okay. So next part, I think we won't derive this. Okay. What I want to tell you is about the concept. So last time when we introduced the line integral, right? We also introduced the arc length function also, right? We introduced how to compute the arc length. Okay, before doing the line integral. Remember or not? I teach you. Okay, maybe I think you guys forgot. So, so remember what's the arc length? What's the arc length formula? Remember this formula or not? Partial x, or partial x partial t squared plus partial y over partial t squared partial z over partial. So this is the arc length of C. Does anyone remember this? Arc length of C. Last time I relate this to the Pythagoras theorem, right? You have to compute the length, you check the horizontal and the vertical. So you extend to 3 dimension, you need to check 3 direction, okay, to give you the line, the length of the line. Remember or not? Okay, and then how we define the line integral? Remember the curtain, the area of the curtain, okay? So above the line, okay, above the line, we put some function, okay? I put some function, and then I integrate it. So meaning I put weight on each point, okay, of the line, okay? Make sense or not? Make sense, the process, okay? I know how to compute the line, and then above this line, there's some weight given by the function, okay, on the line. Similarly, on surface, I need to know how to compute the area of the surface first, and then I put weight above this surface, and then I integrate. Okay, so similar idea. Can get it? Imagine. So above the line, okay, above the line, I put weight, okay, and then now what we do is above the surface, okay, I also put weight, okay, I put weight. So this is the surface integral. We're gonna do it soon. Okay, we try to achieve this. So we need to know how to compute the area of a surface first. Okay, before we put weight above this surface. Okay, similar to the line. We first know how to compute the length of the line first, and then we put weight on top, and then we integrate. Okay. So how to compute a surface? Okay, surface area. So the surface area for a parametric surface, okay, is given by the following formula. Integrate over the length of my cross product. Okay, why suddenly have this length of cross product? Okay, why does it suddenly have this length of cross product? So do you know how to find the area of a parallelogram? You know how to find an area of a parallelogram? Let's say A and B here. How to find the area of a parallelogram? High school, high school. So, A times B, angular. Angle, okay. Let's find the angle between AB. Okay, so how do you use this angle here? A times AB sine theta. Okay, AB sine theta. This one is in high school, okay, because it's just number AB. But let's say I replace A and B with vector. What's this formula become? You need to get the length of the A and the length of the B sine theta. But what is this? This is A, the length of A cross B. Okay, so this is the length of A cross B. Okay, so the length of a cross product give you the area of the parallelogram built up by the two vector. Okay, so this one actually compute the area of some parallelogram. Okay, where does this parallelogram lies? This parallelogram exactly lies on your surface. Okay, this parallelogram lies on your surface here. Okay, so because your line is your general function, general surface is curved. Okay, so you use this tangent vector to make it flat. Okay, make it flat, and then you compute. Okay, so the picture is this. Okay, this is the picture. So your general surface is not a real rectangle. Okay, if it's not rectangle, it's not a parallelogram, you cannot compute it. Okay, so it through this tangent vector here, you make it flat. Remember, tangent vector is the linearization of your function. Okay, if you become linear, it becomes a plane. On the plane, you can do the usual xy computation. Okay, so once you turn it into tangent vector, you linearize your surface. Okay, you make the curved surface become linear. Okay, but you need to take limit to very small, right? So that you can really see the linear. So that's why we take the limit here. Okay, I mean limit in the R, U, and RV. The integral limit here meaning we take smaller and smaller pieces to approximate our surface. Okay. So remember, what you need to remember is how to find the area of a surface, parameterized surface. You need to get your two directional vector, directional derivative vector with respect to u and v. Okay, cross them together and then compute the length. Okay, cross them together and compute the length. This also makes sense, right? Why does it make sense? Double integral apply on what kind of function? Rn to R. Okay, R2 to R. In particular, in this case, is R3 to R. Okay, so if you just cross two vectors together, what do you get? Another vector. Okay, it's not an R3 to R function. Okay, but after you take a length give you what? A number. The number live in R. Okay, so I give you a point, you give me a number. So it's an Rn to R function. Okay, so only this makes sense. Everything will make sense. Okay, everything is well defined here. Okay, any question on this part? Okay, so next, I can provide this solution. You can check later. You can try and do it yourself. So next, if your function can be written as z equals to fxy, okay, for example, z equals to x squared, something like this, then there's a special formula for it. Okay, you can derive this formula, right? You can derive this formula. So if your function can be written as z equals to fxy, how do you transfer it to ruv or rsv, maybe rsy? How do you write this down? Given a function is z equals to f equals to xy, how you give rxy? Thinking. How to give a parameterized surface vector function using z equals to fxy? What are the three coordinates you should put? What does z equals to fxy? Huh? Can you try? Want to try? Want to try? Want to try? So z equal to fxy means what? that is controlled by x and y. So who are controlling x, y? Z is a dependent variable of x and y. X and y are independent. Okay, so x is just x, y is just y, z is controlled by fxy. Okay, so this is how you go between these two forms. Okay, so just now I tell you, given this form, okay, I can find my ax to be what? To be the double integral of the length of the rx cross ry, okay, integral over a. Okay, so this means that you need to show that this cross product here, okay, after you taking length, is actually the square root 1 plus del z over del x squared plus del z over del y squared. Okay, you need to show that this is equal. Okay or not? You want to see, or do you want me to show, or you can try and do? Show? Okay, good. So let's show it. So in this case here, what is Rx? What is Rx in this case? I give you Rxy already, right? So differentiate with respect to x, what do you get? And yet, differentiate this function with respect to x, what do you get? One, 0. Differentiate with f with respect to x. Okay. Similarly, you have ry. It's just 0, 1, differentiate f with respect to 1. Okay. So now we want to take cross product. Okay, let's take cross product of these two. So meaning we need to set out the matrix and then take the determinant. So 1, 0 del f del x and 0, 1 del f del y. Okay, so what's this cross product you get? What's this? Okay, so I, okay, on the I component, you take the minor. Okay, the minor is minus f over del x. Okay, and then j, you take the minor again, del f del y, but you have a cofactor sign, del f over del y. Okay, okay, you get 1. Okay. What's the length of this? What's the length of this vector? What's the length of this vector? You take the dot product between itself, and then you take the square root. Okay. So you take the dot product, and then take the square root. Okay, so what is this? Del f del x squared plus del f del y squared plus 1. Okay, square root. Okay. Is this the same as this formula or not? Same, right? Because f is just z. Okay. So you see where this 1 come from? Okay, because we differentiate x and y with respect to x. Okay. So this is where the 1 come from. Okay. Make sense? Okay, so this is a particular case, okay, of the general formula here. So if you like, you can just remember the general one, and then you can deduce the specific one. Okay. Any question? Okay, no question. So we skip all the that's finding surface area exercise. Okay, next we'll do surface integral. Okay, finally we'll reach the surface integral stuff. Let me see. Is it correct? Yeah, correct. Okay. So surface integral. Last time we learned double integral, right? Double integral, we are cutting on XY plane. Okay. But why we introduce surface integral? Because we no longer want our surface just sitting on the XY plane. Okay. We want it to sit on something that is uneven. Okay. This one uneven. I want to see what happened to the function vector field on this uneven surface. Okay. Yeah. So how do we define the surface integral? Okay. So it's similar to how we define the double integral. So we cut our surface into smaller piece of rectangle. Okay, smaller piece of rectangle. Okay, and then we sum it up, and then we cut it infinitely many. Okay, until I approximate everything. But as I told you just now, this rectangle, right, is not flat. Okay, it's curved. So how to compute this curved surface here? Okay, what we have introduced just now is a normal vector. Okay, normal vector coming from the cross product of tangent vector. Okay, actually that thing is called the Jacobian. Okay, the Jacobian is also a normal vector of something. Okay, so actually, so this curve area of the curved rectangle here can be approximate by our approximate by our parallelogram built up by two unit tangent vector. Okay, yeah. So this is the theorem here. Okay, so the limit is hard to compute, limit of sum. So we have this theorem. As long as you have a parametric surface here, okay, what you have is your area of surface formula. Okay, the length of the normal vector of two tangent vector, and then plus the multiply by the weight function. Okay, so I put a function above my surface. Okay, I put weight on every point in my surface. Okay, so every point in my surface is what? Is given a weight. Okay, it's given a weight fxy. Okay, so this is the formula here. Okay. So if you want to do surface integral, okay, surface integral fxy, okay, then what you do is you scale your area of parallelogram by this function. Okay, function times this area of parallelogram. This area of parallelogram is exactly the Jacobian. Okay, it's the Jacobian that you encountered before. Okay, so because I didn't prove to you, actually the Jacobian is also also accounting this factor of curve surface. Okay, yeah. So in particular, similarly, you can replace the area of parallelogram with this square root of 1 plus del z del x squared plus del z del y squared if your function is a function that can return as z equals to fxy. Okay. So what's the difference between these two? Right. So remember, the single example you need to memorize to remember after this class is a circle, is a sphere and a hemisphere. Okay. If it is a sphere, you can write it as x squared plus y squared plus z squared equals to some radius. But sphere, hemisphere, you can write it as, for example, the positive hemisphere, you can write it as z over a squared minus x squared minus y squared. Okay, so z equals to fxy means this. Okay, z equals to some function in xy. Okay, and then here is arbitrary surface. Okay, so you understand? Understand or not? Okay, so one thing you need to memorize is sphere and hemisphere. Okay, sphere and hemisphere. Sphere and hemisphere. Okay, positive hemisphere. Okay. Yeah, so observe this. So this one is the same property we encountered before. If you double integrate one, okay, over the surface, you just get the area of the surface, area of the domain. Okay, in this case, it's a surface. Okay. Okay, what time is it? 4:90. Can we finish one example and then we go? Yeah, okay. We do one example and then we go. Hey, if Friday extend a little bit longer, is it okay? I'm not sure lah. I'm just a bit worried. Maybe by half an hour to 45 minutes. Can or not? Is it okay? Because I don't do extra class on you. The other class I do extra class on you. So barely can finish. Okay. So I'm not sure. I just beg your permission first. Yeah. Okay. Sure. I mean, in the final lecture, I will give you summary tips, exam tips, and then assignment, discuss assignment. I'm not sure I can finish on time or not, but if cannot finish on time, I will discuss the problem. Go through any problem that you want. Yeah. Okay. And then you should bring any problem here as well if you have any. Okay. Because I leave on Saturday, so you still can message me, but maybe I'll be late on replying. Yeah. Okay. Yeah. So if you want to settle fast, then you need to bring it on Friday. Yeah, I follow Australia. Of course. Yeah, so Australian time now is 2 hours ahead. 2 hours ahead. Yeah. Wow, why you know better than me? 2 hours ahead, yeah. 2 hours ahead. Okay. So like now it's 4:51, so they already 6:51, something like that. Okay. Okay. So let's do this and then we will finish today's. Okay. Finish today's. Okay. So we want to compute. Let's get an example. So if you don't get my explanation just now, it's okay. We will repeat again what we're going to do. So we want to try and find the surface integral of x squared dx, okay, of this unique sphere here. So first thing is similar to what line integral do. We need to parameterize our surface here. Okay, you see that there's only two integral here, double integral here. So that means you only have two variables to play around with, okay, to do the surface here. So what's the two variable you need to build this unique sphere? I think we go through this example just now. We do it for any a, but now a is 1. Right, a is 1. So what's the vector function for this parameterized surface? Right. What's the coordinate we need for a sphere? Spherical coordinate. Okay, so x have to be equal to what? Sine phi cos theta. Okay, sine phi sine theta and cos theta. Okay, we have no rho here because rho is 1 in this case. Okay. So what's the domain for my phi and theta? What's the domain? Phi have to go from 0 to pi. Okay. Theta going from 0 to 2 pi. Okay. Okay, so let's see. Let's go with the definition of surface integral first, and then we will see what else we need. Okay. So how do you imagine this surface integral? Okay, first you need to draw your surface. Your surface is a sphere. Okay, your surface is a sphere. Okay, your surface is a sphere. And then you have a function x squared at every point. Okay, so meaning on the sphere, they carry a number x. Okay, depend on what x it is, you carry that number. Okay, for example, this point is 0, 0, 1. So above 0, 0, 1, what is the number it carries? 0, x equals 0. Okay, right. So here you have 0. So depend on what x you have x squared. Okay, 0 squared and 0. So what's the definition of the line integral? Okay, sorry, surface integral in this case. So we need to turn it into the normal d phi d theta. Okay, you need to turn it into a d phi d theta. But when you turn it into a dA, okay, d phi d theta, what's the contribution from your parameterization? What is that contribution? You need the Jacobian. Okay, what is the Jacobian here? What's the Jacobian? Is the length of your normal vector. Sorry, length of the cross product of your, okay, yeah. Length of the normal vector, correct? But the normal vector is the cross product of two tangent vector. Okay, so two tangent vector here is r phi cross r. Okay. And then your function x squared. So x squared on the surface is sine phi cos theta everything squared. Okay, so meaning we need to compute the two tangent vector here. So let's compute the two tangent vector here. So yeah, okay, let's do it. So r phi is what? R phi is cos phi cos theta. Okay, cos theta sine theta minus sine phi. Okay, r differentiate with respect to theta is what? Minus sine phi sine theta sine phi cos theta and 0. Sine phi. Okay, so then you need to take cross product and then you need to take the length again. Okay, so you need to take the cross product. So let's quickly do it. You can compute on your own and then check whether we get the same answer or not. Okay, so you take the cross product, you get sine square phi cos theta sine square phi sine theta sine phi cos phi. Okay, so the hardest thing is not computing this cross product, but it's the length. Right, you need to take the dot product. You need to take this vector dot with itself. Okay, you need to take this vector dot with itself. To take this vector dot with itself. Okay, you need to take this dot vector dot with itself. And then can you quickly see what happened? You can pull sine square phi out, okay, from two of them. Okay, you get cos square theta, sine square theta, add up to 1 for the first two. Okay. And then what else? So let me write further. Let me compute. So I combine the first two, I get sine phi to the power 4. And then we left with the third term here, third term. Okay, and then we can further substitute sine square phi. Okay, and then we reduce to square root sine phi squared. Okay, and And then in the end, we just reduce to sine phi. Okay, so it reduce to something simpler. Okay, so this is the Jacobian contribution. Okay, this is the Jacobian contribution from your surface sphere. Okay, so, and then you just need to solve the integral here. Okay, you just need to solve the integral. So what's the range of your d phi and d theta? Huh? So phi is going from 0 to pi. Theta is going from 0 to 2 pi. And then you solve this. And in the end, you should get 4 over 3 pi. 4 over 3 pi. You should get it. You should get this 4 over 3 pi. Okay. Any question on this surface integral here? We haven't gone into surface integral of vector field yet, so we will go into next time. And then next time we will introduce the orientation of surface, because vector field is a vector. So you need to remove the vector. So you need to use the normal vector of the surface. Here, there's no vector because x squared is just a scalar field. Okay. Later we will deal with vector field. Scalar. Yeah. Okay. So we will see Mobius band next time. Okay, we'll see Mobius band next time. Any question before we go? Any last question? Question? You still got question? About the project? Oh, okay. Okay, so see you on Friday. On Friday, we will take a photo before we dismiss. Okay, yeah. Huh? Yeah. Huh? Yeah, yes.
是哦，我谈那个ray tracing 的时候，我谈那个ray tracing的时候。